Morning, everyone. Now, we are going to discuss about testing of hypothesis. And uh, First, we start with from some preliminary definitions. So, we have a population, and uh, we have a statement about the population. So, we already discussed about the distribution of some sample parameters or sampling distributions of mean and uh, portions. Now, here also we discuss about the same kind of parameters. Now, let's have a population like students of a particular college. Uh, then I'm interested in the average marks in maths or the marks in mathematics. That is what I am interested in. And I'm unable to contact all the students of the college and collect their marks in mathematics and study about it. So I just take a sample from the population and study the sample and make inference on the population uh, using the information I obtained from the sample. Now, I make a statement about the population or about a parameter of the population, say something like the average or the mean mark of the population is some 60 out of 100. So that's a statement about the population parameter mean. So I just make a statement about the population and have to check the validity of our of my statement based on a sample collected from the population. So I just collect a population or collect a sample from the population, say of size 50, and collect the marks of all the students and find out the average mark of the sample. And based on the value of x bar, say the x bar may have some values like um, 45 or 75 or 59.1 or 62.7, etc. These are all possible values of x bar. Then, based on these values, uh, I make a decision about my statement about the population, like the average mark is equal to 60. So, if we have the value of x bar as 60, then we feel that the statement is true. But what about the other observations? If what about x bar is equal to 59.1 or 62.7 or 75 or 45? Then whether I can accept the statement mu is equal to 60 or whether it is a wrong statement. So these kind of problems uh, are what we are going to discuss in testing of hypothesis in a formal way. So we start with the formal definition of sometimes. So hypothesis in uh, common language, hypothesis is a statement about the population. Like mu is equal to 60, or mu is less than 60, or mu is greater than 60, or mu not equal to 60, etc. So then the null hypothesis, usually denoted by H naught, H naught, is a statement about the population parameter that is assumed to be true if there is convenient evidence to the contrary. So usually this is a statement or null hypothesis is the statement about the population, which usually we check for. And alternative hypothesis is the statement about the population that is contradictory to the null hypothesis and indicate the direction in which the theory would shift if there is not enough evidence in favor of the null hypothesis. So if I have a statement like mu is equal to 60, that's our um, null hypothesis. Usually in practice, the null hypothesis is taken in equality form. Mu is equal to 60, or the standard deviation is equal to 1.5, or the proposition or the proportion of success is equal to something. So that is like P is equal to, say, P naught. So usually the null hypothesis is taken in equality form. That's a conventional method. And the alternative hypothesis H1 uh, will give a direction in which we move if the null hypothesis is rejected or is not accepting. If we are not accepting the null hypothesis, then what will we do? So if our null hypothesis is like mu is equal to 60, that is the average mark is equal to 60, and I collect a sample of size 50 and find out the sample arithmetic mean. And based on the statics, I just make a decision on H naught. Then if what happens if we reject the statement that mu is equal to 60, then that is our alternative hypothesis. This can be either mu not equal to 60, or mu less than 60, or mu greater than 60. So if we reject the null hypothesis, then uh, which among these three statements we are going to accept? So either we can check the validity of our null hypothesis against mu not equal to 60, or we can check the validity of our null hypothesis against mu less than 60 or mu greater than 60. So these are three different situations. So whenever we check the validity of a null hypothesis, first we have to mention what's the alternative. So if we reject the null hypothesis, what is going to happen? That should be specified before we start our uh, testing of hypothesis. That is, even before we take the sample from the population. Then there's a concept of null hypothesis and alternative hypothesis. Then there is a term called significance level. That is the probability of rejecting the null hypothesis when it is true. That is the formal definition of significance level, or it is the level of significance, or it's a probability uh, by which we can reject a null hypothesis when it is true, and we are trying to minimize that probability. And usual values of alpha, the significance level is 5% or 1% or something like that. There's a small probability of rejecting a null hypothesis when it is true. Uh, so the lesser the value of significance, the better our result. Then uh, just remember, alpha and alpha is the significance level, and 1 minus alpha into 100% is usually referred as the confidence level. Both are uh, related in some way. So just try to compare these two terms, confidence level and significance level. Then static is the static computed from the sample to test whether H naught should be accepted or rejected. So first we frame H naught, then we calculate a static. If we are making a statement about the mean, usually we calculate X bar to check the validity of the statement. And if we are making a statement about the uh, proportion, then P bar is the static which we calculate from the sample. And based on the value of X bar and P bar, we make a decision. Then the critical region is the rejection region, is the region of values of test statics for which the null hypothesis is rejected. So if let's have a raw example. If H naught is a statement, as we mentioned about X naught is equal to mu, and we make a region, say 60 is here, is an interval centered at 60, say 60, 55, and 65. Then if the value of X bar fall inside this region, we accept our statement. And if X bar is uh, outside the region, then we reject the null hypothesis and accept the alternative hypothesis. So this region outside the interval is known as the critical region. So that's a simple explanation of critical region. But uh, the region inside this particular interval is known as the acceptance region. Then the boundary values here, something like this 55 and 65, is known as the critical values. But critical values usually we give the critical values based on the significance level. So it is related to alpha. Here, this 55 and 65 are just uh, two values. I just give two values, 55 and 65, and they don't have any relation with the probability or distribution of the statics or distribution of the population or the level of significance uh, or something like that. But in formal setup, we find the values of boundaries of this acceptance region or the critical values based on the significance level, which is obtained from the sampling distribution of our uh, nature of our sampling distribution of X bar. Anyway, uh, that's the concept of critical region. Now, these are the formal steps by which we test a given hypothesis. We start with define the hypothesis like H naught, mu is equal to mu naught. That is our hypothesis. Mu is equal to something like mu is equal to 60. The average mark in the population is 60. That's our null hypothesis. Then we fix alternative hypothesis like mu not equal to 60. The average mark is not equal to 60. That is our alternative hypothesis. There are other options like mu less than 60 or mu greater than 60. But uh, you have to fix the alternative hypothesis depending on the nature of the problem. And here I just fixed mu not equal to 60, 60. Then we have to fix the level of significance like 5% or 1%. So just say 5% significance or in probability 0.05. So fix the level of significance. Then identify test statistics and find the critical values. So here, because we are dealing with the population mean, the arithmetic mean obtained from the sample can be good test statistics to check the validity of our statement about the population mean. So X bar is our statistics and we need a critical value. So since X bar is uh, static, and this static has a um, normal distribution. And x bar minus mu by sigma by root n is a standard normal random variable. Based on those data, we can find out the critical values, and that will be discussed in our next slides. And now compute the value of test statistics from the random sample and check whether it belongs to the critical region or not. So remember one thing, before even starting to collect the sample, we fix our null hypothesis and alternative hypothesis and the level of significance. And only after that, we move on to pick a random sample from the population and calculate the static and find the value of the static and identify the critical values based on the significance level and uh, okay, and the distribution of x bar or the static. Then, based on this distribution of x bar and significance level, we can have a critical region. And if the value of static falls into the critical region, then we reject the null hypothesis and accept the alternative hypothesis. And if it falls outside the critical region or inside the acceptance region, then we accept the null hypothesis and the alternative hypothesis is automatically rejected. So if the calculated value of the test hypothesis belongs to the critical region, we reject the hypothesis. And if the calculated value of test hypothesis uh, is in the critical region, we reject S naught, and alternative hypothesis is accepted. Alternative hypothesis is uh, accepted. So that is how we test the hypothesis. Then error in testing the hypothesis. Uh, there are two kind of error which may happen in testing of hypothesis. If a true hypothesis S naught is rejected, then an error is made, and that kind of an error is known as type 1 error. And the probability of type 1 error is denoted as alpha, the significance level. Then if a false hypothesis is accepted, because all this happens based on random samples, this may happen. And if a false hypothesis is accepted, then we say that that's a type 2 error, and the probability of type 2 error is known as the power of the test and usually denoted by the letter beta. Now, these are the critical regions for a large sample test about or a statement about the mean of a population, and the sample size is large. So the null hypothesis is of the form mu is equal to mu naught, and the alternative hypothesis can be mu less than mu naught, or mu greater than mu naught, or mu not equal to mu naught. These are the three possible alternative hypotheses. And the test statics is we calculate x bar from the sample and we normalize it, uh, since z is equal to x bar minus mu naught divided by sigma by root n is the standard normal random variable. We normalize it and we calculate the value of z. Then based on the value of z, if z is less than z alpha or z is greater than or equal to z alpha, or mod z greater than or equal to z alpha by 2, that's the critical region. If z falls into the critical region, then we reject the null hypothesis. Otherwise, we accept the null hypothesis. And the critical region is identified based on the alternative hypothesis. So the important thing, uh, which is the test statistics, and which is the which is the alternating hypothesis, and which is the associated critical region. Those things should be identified first. Then calculate the value of x bar and then z. So here mu naught is the uh, value of mu against which we make the test. S naught, mu is equal to mu naught. That is mu naught. And sigma is the population standard deviation. N is the sample size. Then if the population standard deviation is unknown, then we can replace it with the sample standard deviation in the case of large samples. Then for a proportion uh, of a population, then and if we have a null hypothesis like P is equal to P naught, then the test statistics is P minus P naught divided by square root of P naught into 1 minus P naught divided by N. So that's again the normalization. Then we have the alternative hypothesis like P less than P naught, P greater than P naught, P not equal to P naught, and the corresponding critical regions Z less than Z alpha, Z greater than Z alpha, mod Z less greater than Z alpha by 2. So the normalization process is the same, uh, x minus mu by sigma, the way in which we normalize a normal distributed random variable into a standard normal random variable. The same thing, same linear transformation or the same transformation is used here. P bar minus is mean P naught divided by is standard deviation square root of P naught into 1 minus P naught divided by N. Then if we have statistics hypothesis like mu1 is equal to mu no, mu2, that is, if we have two samples taken from two populations, and we have to check whether those two populations have the same mean, or if we have to compare two classes in terms of their marks obtained in a particular series examination, then we compare them in terms of average marks. But if the population is a large one, then we have to compare them using the average marks in obtained from two samples. And the sample sizes uh, or sample collected from the population 1 and population 2 may not be of the same size. They are of size n1 and n2. And the population standard deviations are sigma 1 square and sigma 2 square. They need not be the same. And we are checking whether those two populations have the same mean or not, or in other terms, mu1 is equal to mu2 or not. And the possible alternative hypothesis H1 can be mu1 less than mu2, mu1 greater than mu2, or mu1 not equal to mu2. And the critical regions Z less than or equal to Z alpha, Z greater than or equal to Z alpha, and mod Z greater than Z alpha by 2. And if we consider the normal distribution, then Z alpha by 2 is a value in such a way that these two probabilities are alpha by 2, and this is Z alpha by 2, and this point is minus Z alpha by 2. And if the value of Z, not X bar, if the value of Z falls into this particular region, these are the critical regions. If it falls into these two regions, then we reject H naught. And if Z falls into this large region, then we accept H naught. And if the alternative hypothesis is mu1 less than mu2, or is less than or equal to or greater or equal to type, then the critical region is something like this. It is alpha This is 1 minus alpha, and this is our critical region. And this kind of the first picture represent an alternative hypothesis of the form H1 mu not equal to mu naught, or mu1 not equal to mu2, or P not equal to P naught. That kind of a test is known as a two-tailed test, in which the significance alpha is distributed in two tails. So it is two-tailed test, and this is a single-tailed test. If the alternative hypothesis is um, mu1 greater than mu2, um, this is our um, single tail test, or the critical region. And if we consider our alternative hypothesis like H1 mu1 less than mu2, then the critical region falls in the negative side of the distribution here. This is minus Z alpha by Z alpha by 2, and this is our critical region. Oh, here we missed the minus sign also, I think. Um, so here, um, one tail test, if the alternative hypothesis mu1 less than mu2, it is Z less than minus Z alpha. So there is an error here. So let us correct it. Um, Here it is minus Z alpha. So I think we have the same mistake in our previous slides also. Here also, if H1 is mu1 less than mu naught, then it is minus Z alpha. That is one tail test. The tail probability is here. It is 0. If we calculate Z alpha, then this is Z alpha, and this is the probability of alpha. And if Z falls into this particular region, we reject H naught. And if mu is greater than mu naught, then Z is greater than Z alpha. And in that case, the alpha probability is in this particular tail edge. And this is our Z alpha. And so if this is our critical region, for critical region of Z, then I think the same mistakes is all happen here also. This value is minus Z alpha. Then here we compare the proportions of two populations, and anyway, here also we have made the same mistake, minus Z alpha. Okay, anyway, here we consider proportions of two populations, and the null hypothesis P1 is equal to P2, and the test statistics is Z is equal to P1 bar minus P2 bar, where P1 bar and P2 bar are the proportions calculated from the first sample and the second sample of size N1 and N2 respectively. Then Z is P1 bar minus P2 bar divided by square root of P into 1 minus P into 1 by N1 plus 1 by N2, where this P is calculated as x1 plus x2 divided by N1 plus N2. Then we calculate the statics and check whether it belongs to the critical region or not. Then all this happens when the sample is a large sample. When we have a small sample, If the sample is taken from a normal distribution, then uh, x bar minus mu by sigma by root n is a standard normal random variable. Uh, if the sample is taken from a normal distribution, then x bar minus mu divided by sigma by root n is a standard normal random variable if x bar is taken from a normal population, even if n is less than 30. But if the value of sigma is unknown, then we can replace it with the population standard deviation S bar, then divided by root of n. That's a standardization process. But there is a problem. If you calculate x bar minus mu by s by root of n, then it need not be a normal random variable. It is a student's t random variable. And a student's t random variable is again a random variable which has a probability density function with a bell-shaped curve as the probability distribution, but the skewness of this particular curve is different from that of N01. It depends on the sample size N, and which is referred as, or which is referred as the degrees of freedom of the distribution, and it related to the sample size N. If we have a sample size n, then x bar minus mu by s by root of n will follow a student's t random variable with degrees of freedom n minus 1. This student's t random variables, its values are available in your statistical table. You can check your statistical table to find the student's t values corresponding to the significance level and the degrees of, and that will give the value of t n minus 1 alpha or alpha by 2. So that will give the students t probabilities, and using that, if we have test statistics of if you have a null hypothesis of the form mu is equal to mu naught, then the test statistics is x bar minus mu naught divided by s by root of n, whereas is the sample standard deviation. Then we have the critical regions, um, and here also this slash is an error, and this one is minus. H1 is the null hypothesis or the alternative hypothesis mu less than mu naught, then the critical region is t less than minus tn minus 1 alpha. And if mu greater than mu naught is the alternative hypothesis, then t greater than tn minus 1 alpha is the critical region. And if the alternative hypothesis is modulus mu not equal to mu naught, then the alternative hypothesis is mod t greater than tn minus 1 alpha by 2. Then these are the critical regions associated with each of the test statistics. So our process, uh, first form H naught, then form H1, fix the value of alpha. Then depending on H naught, whether H naught is a statement about the mean or proportion, then based on whether the sample size is large or small, whether sigma is known or unknown, fix the test statistics, either the value of Z or the value of T. Then based on H1, uh, find out the critical region either as Z less than Z alpha or Z greater than Z less than minus Z alpha, Z greater than Z alpha, or mod Z less than uh, Z alpha by 2, or T less than T minus T alpha by 2 in the corresponding degrees of freedom n minus 1. and so on. Then find out the value of the test statistics x bar or p bar. Then normalize it uh, and check whether it belongs to the critical region or not. If it belongs to the critical region, reject the null hypothesis and accept